The complex conjugate pair theorem says that if we have a polynomial with real coefficients and a plus bi is a root of the polynomial, then a minus bi is also a root of the polynomial function. In other words, non-real roots of a polynomial function come in conjugate pairs. So here we have an example problem that uses the complex conjugate pair theorem. Write a polynomial function of least degree, smallest possible degree, that has real coefficients, a leading coefficient of 1, and the zeros 5 and 1 plus 3i. Well, given that we have a polynomial with real coefficients, by the complex conjugate pair theorem, 1 minus 3i is also a root. So this means that the minimum degree of the polynomial is 3. This would come from multiplying out the factors x minus 5, x minus 1 plus 3i, and then x minus 1 minus 3i. So now I have a little shortcut to teach you for multiplying x minus 1 plus 3i and x minus 1 minus 3i. Instead of doing an expansion box, I'm going to teach you a little algebra shortcut over here. And you can verify this by multiplying it out. This is going to be really handy. If you are multiplying x minus a plus bi by x minus a minus bi, what you are going to get is x squared minus 2ax plus a squared plus b squared. So that means if you're multiplying x minus a complex number by x minus the complex conjugate pair, you can use this as a formula to immediately write down the resulting quadratic. So over here, if we look at x minus 1 plus 3i and x minus 1 minus 3i, a is 1, b is 3. So that means that this quadratic is going to be x squared minus 2x, because a is 1, plus 1 squared plus 3 squared, which is 10. So again, a squared plus b squared, that means we say 1 squared plus 3 squared, 1 plus 9 is 10. Over here to the side. And it's negative 2 multiplied by 1. It's negative 2. That's the coefficient of the linear term. Then we multiply that by x minus 5 to get the polynomial of minimal degree. So that will give us x cubed minus 2x squared plus 10x combined with negative 5x squared plus 10x minus 50. That combines to x cubed minus 7x squared plus 20x minus 50. So you can see that it saves us a lot of time if we use this algebra shortcut. Just remember to identify what real number is A and what real number is B. And you can use this little formula. So let's do this again here. We want to write a polynomial function of least degree that has real coefficients, a leading coefficient of 1, and the zeros 4 and 2 plus I. Well, by the complex conjugate pair theorem, two minus I is also a root. So the minimum degree is 3. And this would come from multiplying out the factors x minus 4, x minus 2 plus I, and x minus 2 minus I. Well, let's use the little algebra shortcut to make our lives easier. Remember that we're going to get x squared minus 2ax plus a squared plus b squared. Well, a is 2, so negative 2ax is going to be negative 4x, and b is 1, so a squared plus b squared is going to be 2 squared plus 1 squared, which is 4 plus 1, which is 5. So we get x squared minus 4x plus 5 when we use that little algebra shortcut. Then we distribute, which gives us x cubed minus 4x squared plus 5x minus 4x squared plus 16x minus 20, which gives us x cubed minus 8x squared plus 21x minus 20. Now we have one last example. Given that 3i is a root of f of x equals x squared plus 5x cubed plus 13x squared plus 45x plus 36, find all the roots. So the first thing to notice is that we have all real coefficients. This means that by the complex conjugate pair theorem, negative 3i is also a root. So that means that x minus 3i and x plus 3i are factors. And if we multiply x minus 3i by x plus 3i, we get x squared plus 9. This is the opposite of what we were doing before when we were factoring the sum of squares x squared plus 9. If you've forgotten how this works, you can use an expansion box to see that x minus 3i multiplied by x plus 3i is x squared plus 9. So then, to find all of the roots, what we can do is take this quartic polynomial and we can divide by x squared plus 9. There's something else we could do if we prefer. We could synthetically divide the coefficients of f by 3i and then take those coefficients and divide by negative 3i. That's another way to do this problem. I think it's a little easier to just use polynomial long division to divide this quartic polynomial by x squared plus 9. So I'm going to write this out. divide. So I get that x squared is the first term of the quotient polynomial. I multiply through, subtract. I bring down 5x cubed plus 4x squared. The remaining terms. And then the next term of my quotient is 5x. I multiply through and I get 5x cubed and 45x. I subtract off and I bring down 4x squared and 36. Then the final term of my quotient is 4. And I subtract off 4x squared and 36. So that leaves me with x squared plus 5x plus 4, which factors as x plus 4 multiplied by x plus 1. So I can factor this polynomial as x squared plus 9 multiplied by x plus 4 multiplied by x plus 1. The vocabulary here is x squared plus 9 is an irreducible quadratic factor, meaning it cannot be factored into linear factors with real coefficients. And x plus 4 and x plus 1 are both linear factors. So that's the factorization, and the roots are 3i, negative 3i, negative 4, and negative 1.